Welcome. Welcome to this talk on cyclic instabilities are circular crested weirs. My name is Hubert Chanson, and I'm based at the University of Queensland in Brisbane, Australia, in the east coast of the Australian continent. At a weir on spillway crest, the relationship between the volumetric discharge, PQ, on the head above crest, H1 minus P, is often dubbed the Weir equation. In this Weir equation, the dimensionless coefficient CD is a discharge coefficient. As it is dimensionless, it has no units, and it characterizes the hydrodynamic efficiency of the crest design. CD is about unity for broad crested weir, is less than 1 for a sharp crested weir, and is greater than 1 for rounded weirs, with values of 1.28 for an OG crest hard design head on a tall weir, and values that may reach and exceed 1.4 to 1.6 for a circular crest. Also highly efficient, the circular crest may however experience instabilities with massive data scatter of the rating curve illustrated on the right, based upon a multi-lab exercise with all the data regrouped in the red dashed area, and one dataset in particular in black. Subsequent work at the University of Queensland highlighted that the lack of ventilation led to hysteresis, non-linearities, and cyclic flow behavior, as illustrated on this graph on the bottom left. These three datasets show experiments conducted for a constant flow rate, looking at the variation with time of the air cavity volume over 30 minutes. A 0 value means there is an attached nappe, no air cavity, and any positive value means that there is a nappe detachment. So, what does it mean physically? Let us look in a movie what is the meaning of these instabilities. The movie presents a time lapse of the cyclic overflow pattern above a half-round circular weir. The experiment was conducted at the University of Queensland in the hydraulics laboratory of the School of Civil Engineering. The movie presents a side view of the nappe overflow. Sometimes the nappe is attached to the weir, and the flow streamline presents a marked curvature highlighted by the free surface that is the streamline itself. Other times, like now, the nappe is detached with an air cavity underneath. The experiment was conducted with a constant flow rate, left constant for several hours before, and remaining constant for the full duration of the recording. With a constant flow rate, we would not expect to see such a drastic change in nappe overflow patterns. The changes are caused by the absence of ventilation of the nappe and associated non-linear hydrodynamic instabilities. The time-lapse record includes a frame every half a second for 60 minutes, and the movie is replayed at 20 frames per second. That is, the movie speed is 10 times faster than real time. The accelerated movie replay emphasizes the cyclic nappe overflow pattern. The cyclic transient instabilities cause very rapid change in hydrodynamic properties upstream and downstream of the weir, as well as transient loads and vibrations on the weir structure itself. During a cyclic pattern, the formation of the air cavity occurs very rapidly, often with loud noise. It is followed by the progressive filling of the air cavity, then the air cavity disappearance, and again the sudden cavity reopening into a large cavity while keeping a constant flow rate. The periods of the cyclic pattern were typically between 3 to 10 minutes, although some unusually wider range of periods, from 1 to 12 minutes, were observed in this laboratory experiment. What now? We just saw the sudden cavity opening. the cavity will progressively start to fill. As the air cavity becomes smaller, the streamline curvature becomes more marked above and immediately downstream of the weir, and then we may have some partial cavity opening. Note the fluctuations of the upstream water level linked with the cavity formation and cavity disappearance.